Okay, thank you for the opportunity. I'm glad to speak here. Thank you, Jack, for inviting me and my professor give me the opportunity. And well, good afternoon for attendance in here. So today's topic is about the SmartTB5, and this is about combining the tiny machine learnings and small chips like Arduino 33 PLA Sense. And the title is a 5G-enabled mobile robot powered by the TinyFusion AI modules. And actually, this work still working in our lab. Before I continue, I would like to introduce my name. My name is Anton, and from the Minci our lab name is a Protocol Analysis and Signal Size Laboratory, and my supervisor is Professor Ichitong. And let's we continue about the outlines, and we have introduction here, literature review, methodology, experiment result, and conclusion, future work, and Q&A. So basically, when we do some work, we have searched and combined what is actually people need. So for our backgrounds, in the background is talk about autonomous mobile robots, critical component in modern intelligent systems. So based on the global market, autonomous mobile robots, or the EMR, is projected to reach 158.2 billions by 2023, and growing for the CAGR is 20.8% from 2023. This research is based on Allied market research in 2023, and adoption of the EMR is not just only for the one place, but it's many places. It's like on the warehouse or the hospital, and yeah, we can see in right now is many places adoptions about the EMR, and yeah, in this example is about the logistic and warehousing like Amazon's DHL, smart cities, petrol delivery, waste management, and healthcare, or in the hospital delivery. I heard in here in the hospital is Changkung Hospital is already have applied for the healthcare using the EMR. And in here, we will explore about the EMR component through the academic example, because we work on research. And one kind of the example is about the turtlebot. And this is the example of the turtlebot, and we can modify, we can try machine learning model and apply it here. Actually, this robot is we can modify and we can try by error. So this robot is based on NVIDIA or Raspberry, and we can try to modify it like this. And inside of the robot is running by the robot operating systems. We can call the ROST. This is robot operating system, but actually this is middleware. So not just only not the real operating system, but it's running inside the operating system. So we have installed the Ubuntu and then running upper the Ubuntu. And today robot platforms are portable, but they mostly rely on the one computer to do everything. Imagine we have the power computer, but to run one task, the small task, it needs more resource and need more power. So in here we try to research how can reduce the power or resource in here, because one kind of the script or the small script need running of all the CPU thread or something. So we have tried to figure out about the centralized AI in mobile robotics, and most autonomous mobile robots rely on the centralized systems such as Raspberry Pi or Jetson Nano to handle sensing, perception, and control. And this is the example. We have the LiDAR sensor, and the LiDAR sensor is running in the Raspberry Pi, and this will be run by the centralized computing. And yeah, These systems are simple to implement but face practical drawbacks like high power draw, one kind of some script running and need the high power in here, and bottleneck under multitasking. When we have tried to run a AI model and combine with the SLAM or AI interference, it's most of like hang or we need restart. And the third is vulnerable to single point failures. So the next is about the cloud-based AI in mobile robotics. And some robotic systems reduce local competition by sending data to the cloud, where decisions are made remotely and returned to the robot. And this is the another options when try to running some models, sending by to using the cloud. And this architecture is used in the applications like surveillance, drones, warehouse plates, remote monitoring bots, and yeah, also face some drawback like latency. We have tried using cloud processing, but yeah, this one, latency issues due to round trip delays and dependence on the stable connectivity. It must need stable connections and risk of failure in network dead zones. So we have a sensor here and capture the raw data using Raspberry and send the cloud processing. And then make some decision and send back to our small computer. So the problem is here. Sometimes the signal is not very well, so the delay happen here. And in some situations where we wonder, could this be better? We have tried to apply this small like Arduino device to embed to our Raspberry Pi, and we have some assumption here about the power consumptions and cost optimizations and lack of modularity. And even portable platform like Raspberry Pi or Jetson Nano can face critical limitations in real-world robotics. And it's about the power consumptions. Some Raspberry Pi is need 5 until 8 watts, and Jetson Nano is 10 until 15 watts. And when the running SLAMs, navigation, and AI simultaneously can be overloaded by the CPU. And high processing load, sometimes heat, power drain, and performance drops. This already happens when we have tried some navigations and combined with the AI, and not idle for 24 hours or battery power systems. And for the cost optimizations, upload basic sensing like sounds, light, or motions from the Raspberry Pi to smart sensor, reducing the CPU load and power usage. And we talk about the modularity, how in one system can be filed entirely in the main board or crash. Sometimes when we try the SLAMs or navigations and combine the AI, yeah, this happen. It's filed entirely. When they file entirely, we must reboot our robot and start again. And modular sensor can make local decision independently and more scalable and maintainable in multi-robot setups. So this challenge leads us to explore a modular sensing architecture called small, task-specific processor support rather than replace one powerful central brain. So this is our question in here. So why our motivation to try small device and combine to such as Jetson Nano or Raspberry Pi. Even the Raspberry Pi or Jetson Nano right now is powerful computer, but sometimes this happen. So our proposed solution is like here. We have table here. So I have already explained before about the traditional approach, like one big brain using only small computer or Raspberry Pi or Jetson Nano. And cloud-based approach is data is sent to the cloud after processing, then decisions are made remotely and returns. And here, we have tried the distributed edge approach, and we call it the SmartTB5, but this is it centers a small AI chip or using the tiny machine learnings and making early decision before sending into the robot brain. So the scheme is sensor, tiny machine learning, or small computer like Raspberry Pi, and decisions, then do actions. So finally, we have our motivation or hypothesis is integrating specialized like tiny machine learning modules near sensor with a central processor such as Raspberry Pi, improve the efficiency and responsiveness, and for the mobile robot in handling specific sensing tasks. So before we continue, I would like to introduce about what inside our robots. In our robots have we call Turtlebot 3. The robot is from the Korea and we can modify here, but this based on the robot operating systems. Yeah, every robot right now is running using the robot operating systems. So we call it ROS. ROS is some like middleware, and this provide a great software framework and hardware software code design leveraged by the robotics community. And this ROS is like framework run over the operating systems and provides services such as hardware abstractions, low-level device control, implementations of functionality, message passing, and packet management. So ROS is actually runs over the Ubuntu operating systems, and this is like middleware. Sometimes middleware, as we know, is like Java, but in here is focused on the robot management. So right now, the ROS version Hub 2 is about the ROS 1 and ROS 2, but the ROS 1 is this year is end of the support in the last May. So the last May of the ROS 1 is about ROSnotics, but this is end of life, and most of the kinds of ROS developer or ROS community encourage of using of ROS. We have migrated to ROS 2. But ROS has become the de facto standard of robot software development, and this will be enabling modular designs, simulations, and hardware abstractions. While the robotics community is gradually transitioning to ROS 2, most academic research still relies on ROS 1 because its proven reliability and large repository of existing package. Some of the research is still using the ROS 1, and some package is still stable in using the ROS 1, but this year is end of support. And this is the architecture about ROS 1 and ROS 2. This ROS 1 is focused on this, using the master and node, and ROS 2 using the data distributions layer. And the ROS 1's based on the Linux and have the middleware like TCP, UDP, and then client library. And to start the ROS 1 using the ROS core or the master, and then we can start our applications. Our applications like Node, and some Node can communicate each other. But for the ROS 2, they're using the data distributions. So this is the operating systems, and this is the data distributions using the some API and like abstract layer, client library, and then Node. So when we start our robot, we not start our master again because it's already start if we using the ROS 2. And this is the example. So I will just take one of the ROS 1, for example, because our research is still using the ROS 1. And this is the ROS 1 using the master node to manage communication between publisher and subscriber, and nodes register with the master. We start the topic into topic info so they can connect directly and exchange the message. So this is the example. This is the master. Yeah. When we start our robot, we must start the master. This is like manage all nodes and manage all the applications, robot applications. So the example, when I move the robot using the keyboard, it will be sent here, and under the master will directly move the robots, and the keyboard and the position of the robot is node. So in here, the master will be manage all of the applications. So we continue with the tiny machine learning. So after we using the ROS, we trying to using the tiny machine learning. So the tiny machine learning is the development of the machine learning models on the ultra low power microcontrollers and edge device, and it enables AI processing directly on the sensor and reducing latency, network usage, and power consumption. This is the one example of Arduino 33, and inside the Arduino or microcontrollers have the sensor. So we run up the tiny machine learning here, run on device, and work with the platform like TensorFlow Lite for microcontrollers and edge impulse, and ideal for application in IoT, robotics, and wearable device. So how the tiny machine learning work is like this, using pruning. This is the original network, and in the pruning have a train connectivity, prune connections, and train weight, and then do some the quantization to make the model smaller and run in our microcontrollers. In here, in the quantizations of the cluster of the weight, generate codebook, quantize the weight with the codebook, and retrain the codebook. And then after we make the model smaller, we do the Hofmann encoding to make a model running in our microcontroller. So in here we have the encode weight and encode index. Also in the tiny machine learning, we know about the model distillations. This underlying knowledge for that larger network have some sparsity or redundancy with the models. Will large network have the high representational capacity? If the network capacity is not saturated, it could be represented in small network with a lower representation capacity. So when we do some making our layer network is like this using the mode distillations. So maybe I will skip this ones, and because to have spend time. And after that, we have do the quantizations. This focus on make model smaller. So quantization means that when we have a many layer, we have prunings and make it simple. So prunings, it means that remove the unimportant connections and sometimes neurons and making the network smaller and faster. And the quantizations reduce the precision of weights from the 32-bit float to 8-bit integer. So they can uplist the memory but keep similar with the accuracy. Yeah, after we do some of the quantizations, we have to do the compilations. In here, we have model has been quantized and encoded. It will be converted to format can be interpreted by some form like neural network interpreter, and the most popular of which probably TensorFlow Lite is like 500 kilobyte in size, and TensorFlow Lite Micro is 20 kilobyte in size. So we began up the 8 processings because we already said before we have comparisons using the one brains, cloud computing, and right now it's 8 computing. 8 computing means that we have our small device and we didn't send the data to the cloud, but we process in our local, but using another helper. Yeah, like us using the Arduino and combined with the Raspberry. And we hope this device can run the edge computing. So edge processing perform computations close to where data is generated on local device, such as sensor, microcontrollers, and gateway, rather than relying solely on remote cloud server. So this is the comparisons: cloud, fog, and edge. So cloud is like centralized data center handling to large-scale computations. And fog is intermediate nodes providing regional processing and aggregations. Yeah, and edge. We have worked in this one, edge device. So performing real-time processing near the data source, reducing latency and bandwidth use, and reliance on the constant connectivity. So we hope that we running the edge device, many edge device, we can group and we can specific the task, doing some tasks, and with the lower power consumptions. And in our research, we use edge impulse, this one. Yeah, edge impulse is like training with the online compiler, and this edge impulse platform for building, optimizing, and deploying machine learning models on the edge device, from microcontrollers to powerful edge hardware. So by enabling the AI processing close to data source, it reduces latency, lower bandwidth usage, and improve reliability. So in our SmartTB5, edge impulse allows smart sensor to run optimized tiny machine learning models locally and sending only essential data to robot brain. So this is the example of the edge impulse that connect the machine learning development with edge deployment, and it supports cameras, gateways, sensor, and other hardware. So I will skip this one. So focus on our methodology. This is the methodology. We have tried to combine our Raspberry Pi to microcontrollers, and this using the middleware like X Impulse, and then process with the cloud, and we put our model in here. And this is integrations. Oh no, the time. So this is the integrations. So this is the microcontrollers, and this is about our Raspberry Pi. So we will talk each other, and yeah, the small device will be focused on here. I make sounds, motion, and environmental, and ROS focus on the navigations. So we can sparingly divide or sharing the resource. And this is the system workflow. Maybe I will skip this one. It's like the basics: start, sensor data, tiny machine learning interference, data functions, and robot actions. And this is the evaluations. So this is our experiment result. So we take the data sets using the edge impulse. It's very help us to collect the data and make the data. So in our small research, we have collect like traffic signs, like turn left, turn right, and no labels, just only 3 labels. And the characteristics like this, varying image with the blur. We take the picture using our the Edge Impulse website, and we have tried to training in here using the Edge Impulse and also label. So for the training, we have processed like this, create the impulse in the Edge Impulse, and after that, we have do the training. We have set up some parameters, and for the training we use of the 100 and learning rate is 0.001, and the result in here. So the result is small because our data set is small. We have just tests for capture the data and try to training. To improve here, we capture like 80 more image and do some labels. So this is the setup look like. So we have set in here Arduino Sense 30, Arduino 33, and Raspberry. So we have communicated with the main ROS processing in here using the URRT and have communication each other. And this is the detections. We using the robot operating system to capture the image. Sorry. We exchange the data with the robot operating systems, and we have tried to capture the image, and this is the result. We have tried to exchange and get the data. So the data is string, and yeah, maybe I cannot zoom. Yeah, in here, well, I didn't make it clear, but actually we can exchange the result, and the ROS is receive the data after capture some of the traffic sign. And the processing is using the small Arduino 33. So actually it's work, and it's already work for building the small model to the Arduino and trying to process with ROS. And yeah, another lab member also do it for the testing with the inertial measurement units, and we want to combine with the robot operating systems with the lower resource. So they have do some gyroscope readings and magnetometer readings, and we have plans to combine these ones. So the small device can run of all of the sensor data, and the big one is focused on the navigation and simulations. So this is the conclusions. So the proposed SmartTB5 framework successfully integrated tiny machine learning sensor with the ROS-based central processor. And current detections accuracy is limited due to small dataset size, lack of data cleaning, and image variability. And detection latency is still high, 3 until 5 seconds, with unstable for real-time robotics, especially when using the real-time camera. This problem is only in the compressed image. We can compress more and can capture more better. So the future work is improve the dataset quality with the cleaning, augmentations, and balance rentals, and optimize tiny machine learning models, inference speed for the faster response times, and explore the multi-threading. This one is our work right now, and asynchronous communication between edge unit and ROS for reduced latency. So, still have time. So I just want to introduce our lab. Maybe it's just only quick review. So our lab is named the Protocol Analysis and Signal Test Laboratory, and my professor is Professor Richard Tung. And this is my lab member. Focus on robots and ESP33 modeling, quantizations, and robots. And I'm glad to also say hi to my lab member in here, Mike and Xiang. And yeah, this is the lab architecture. We have the 5G device and running in the 5G device and private 5G network call box. We have also work in here. And yeah, we also work for the 5G CSI and 5G smart pole. So I think this is enough, and thank you.